So, there's two things that you really need to understand before we start talking about the intake system. The first thing is that the engine's speed is controlled by limiting the amount of air flowing into it. So it's not controlled by fuel, it's not controlled by sparks or timing. When you put your foot on the throttle in the car, what you're doing is controlling the amount of air getting into the engine. The second important thing is that the air flowing into the engine is often the constraint on performance. So an engine is limited in its performance and its speed by the amount of air that it can bring in. Often we can deliver enough fuel, the spark is strong enough, but the airflow is the limiting factor. And that's why the intake system is super engineered and fairly complex. The other thing to think about is that today we're talking about fuel injection systems. So with a fuel injection system, the ECU, or in our case we're going to call it the PCM, the powertrain control module, controls the fuel delivery. So fuel injection is controlled by the computer, and the computer needs to look at various inputs to understand how much fuel to put in there. Those inputs, a lot of them, the more important inputs, are in this system. So as we work our way through from the air flowing in here through the inlet all the way around this system and into the cylinder head, we're going to come across various sensors, and those are super important for actually metering the fuel, because, as I kind of inferred earlier, the ECU matches the amount of fuel to the amount of air coming in. What we'll do is we'll take a brief look in this introductory video at the various components that we've got along the way, and then in later videos we'll look in much more detail at those components. There we go. We'll follow the journey of the air right through from the entrance of this system to the engine. Now, the air makes its way in here into this air inlet duct, which sits in the engine compartment just inside the wing and sucks in fresh, clean air. And the source of suction, let's not forget, is the piston on its downward stroke, on the induction stroke. That pulls air all the way along this system into the engine. So we have our air coming in here, travels along this duct, and makes its way into the bottom of the air box here. So we've got an air box or an air cleaner. The air travels into the bottom, and if we lift the top off, we have an air filter inside here. So the air goes into the bottom, travels up through this filter, which cleans the air, into the top of the air box. And in the top of the air box, we have a temperature sensor here, which reads the temperature of the air. So that's called an IAT sensor, inlet air temperature sensor. Next up, we come through the box here, we're coming out into the hose, and we travel through a mass air flow sensor. So the mass airflow sensor, the MAF sensor, reads or detects the volume of air traveling through this system. Next up, we're moving, let's rotate our engine here so we can see. Next up, we're traveling along this hose, and along this hose we have a chamber down here, which is a resonator that cuts down on the amount of noise created by the intake system. Then let's rotate some more and come forwards. I've removed the radiator so you can more easily see what's happening. So as we come across our hose here back over to the intake side of the engine here, we come to the throttle body. So the throttle body, let's pull this off. In fact, let's pop this entire system over here. I've missed a bit. Let's rewind slightly, come back along our pipe. We have here, on the intake hose here, we have a connection which goes into the top of the cam cover, and this is a source of fresh air for the engine. It's part of what's called the positive crankcase ventilation system, PCV system. We'll talk about that in a later video, but just know that this system pulls air, fresh air, out of the inlet hose here. As I was saying, we come across to the throttle body here. Let's just pop this off and move this out of the way for a minute. What you can see on the throttle body is this is the method of control of the engine speed, basically, and we have in here a flap which is controlled by the driver. So we have a cam here which is controlled by a cable that runs all the way to inside the car, where the throttle pedal would be down here and as you push on the throttle, it moves this cable, a bit like a bicycle brake cable, pulls on the cam there and controls the throttle valve which is inside the throttle body. So that opens up to allow airflow. So normally the valve is closed, minimal air is making its way through. As we push on the throttle, it pulls the cable, opens the throttle body. From the throttle body, we then come in to the manifold. This is the intake manifold, and the manifold basically just distributes the air to the cylinders. So we have 4 cylinders, it just channels this air into 4 different cylinders equally. And on this vehicle, the fuel injection system fits to the manifold here and injects fuel just before the inlet port of the cylinder head. So it just injects that fuel just before the intake valve of the engine, which then travels into the cylinder. We also have on here a hose that connects to the PCV valve that I mentioned earlier, which is a method of ventilating the crankcase and the engine block. On the back here, we have a pipe which is a source of vacuum for the brake system. So with the brake system, the vacuum is used to make it easier to apply the brakes, and that vacuum comes from the intake manifold. We also have the EGR system on our intake manifold here. The EGR system is a method of recirculating exhaust gases back into the intake and burning those exhaust gases inside the cylinder to reduce emissions. So the EGR system, we have the exhaust over here. The EGR pulls exhaust gases through. It comes into an inlet here on the back of the manifold, travels through the manifold, and at the front here we have an EGR valve which controls whether those gases are recirculated or not. And we have an idle air control valve here which determines the amount of air that is passing through the throttle body when the vehicle is idling. So that was basically just a high-level summary. We have air travelling in from here, travelling through various sensors along here into the intake manifold and into the cylinders. Before we move on to talking about the various components of this system in detail, I want to cover off just a couple of quick general points about the air intake system. So we've talked about how the amount of fuel is determined by the amount of air flowing into the engine, and the amount of air is controlled by the throttle, and the ECU then looks at that amount of air and adds the amount of fuel to match. Now, the intake system generally is all about what's called volumetric efficiency, which is how efficiently are the cylinders being filled with air. So if you imagine as the piston moves down, it creates this void that we want to fill with fuel and air, and volumetric efficiency is a measure of, let's say, we have a cylinder with a capacity on this engine 400 cubic centimeters of space in there. Volumetric efficiency is how many of those cubic centimeters have we managed to fill with a mix of fuel and air. So if we filled, say we have 400 cubic centimeters and we put 300 cubic centimeters of fuel and air, it's 75% volumetric efficiency. It's a very important number, and the design of this system is all around flowing air into a cylinder. The closer we get to 100% or even above on a forced induction engine, where you're ramming air and air particularly into the cylinders, you may get above 100% volumetric efficiency, so more than 400 cubic centimeters of air into a cylinder. We've got an episode on volumetric efficiency, VE. Let's trim that down so I don't trip over my own tongue. We've got an episode on VE coming up, including the maths. So with the maths for volumetric efficiency, I can tell you that this engine on a Miata 1.6 litre engine takes about 34 litres of air per second at 3000 RPM. And that is an enormous volume of air. 34 litres of air per second making its way along this system and into the engine. The other important thing to bear in mind is that when we talk about air, we discuss air because that's what we're dealing with. That's all around us here. There's air everywhere. But what we're interested on the engine is oxygen. It's oxygen that's actually being used inside the cylinders here. So inside a litre of air, it's about 21% oxygen. So the oxygen is what we're interested in, but our measurements and what we discuss is air. It's just important to bear that in mind, that oxygen is what we're talking about. Now, the other thing with air is that its density, the amount of air in a litre of space, varies. So if you imagine, we draw a box here, and that box is 10 centimeters by 10 centimeters by 10 centimeters, 1 litre of space, or even if you just take an empty litre bottle, the amount of air in there varies depending on pressure, the altitude that we're at. The higher the altitude, the less air there is in a litre of space. And it varies in relation to temperature. So the warmer it is, again, the less air there is, the lower the density of air. And that means that if we take a litre of, I refer to this as a litre of space, and that is kind of the way you should think about it. But if we were to take a tub, do we have a tub? Let's find a tub. Here's a tub. Here we have a box of air. Now, we're down here at sea level. There's a certain amount of air in this box, which means there's 21% of the air in this box is oxygen. So we've got a certain amount of oxygen. If we go and climb a mountain, we go up to the top of Everest, then we have less air in this box, less oxygen, because the pressure is lower. Likewise, if we're sitting down at sea level and we heat this box of air up, again, we have less oxygen in the box because air at a higher temperature has a lower density. So you have less molecules of air, less parts of oxygen in this box. Those are two important things with air intakes. Are that pressure? Well, we're constrained by the altitude that we're at, so there's not very much we can do about that, except for using forced induction, which increases the pressure. But also temperature. So we need to pull in cold air. That's what we're looking for here, cold air. If we pull in warm air, for example, from next to the exhaust, it has less oxygen in every litre of that air that we send into the engine. So those are a couple of extra constraints. And the other thing, one more thing, just one more thing. We talk about that the air is pulled in by the downward stroke of the piston on that intake stroke. That's a nice simple way to think about things, and in some ways it's true. At low engine speeds, if you imagine our piston moving up and down like this, or you're pumping an airbed, that kind of speed, of course, that's what's happening. That downward stroke is what's generating the pressure differential at low engine speeds. Once you get up to higher engine speeds, what happens is, as the flow of gases is somewhat mysterious. It's a little airy, if you'll forgive the pun. It doesn't flow in a very imaginable way. Air tends to pull other air along and it floats. And if you see a cloud of smoke, you'll see that air continues to move and it has momentum and it has some essence to it. That's what's happening in the engine, is when the piston moves down, it pulls in some air. When the piston moves up, it pushes hot exhaust gases, boom, out through the exhaust ports. And the movement of those exhaust gases actually pulls in fresh air across the engine. So what happens is the exhaust gases leave and they create very high pressure on the way out, and they leave low pressure in the cylinder because actually those gases have kind of boomed out and they're carried by momentum. And in fact, they're pulled along by the previous exhaust gases that left the cylinder before them. And those gases are pulled by the cylinder before them. So you have like almost a fluid chain coming through where intake gases are being pulled into the cylinder by exhaust gases leaving. Now there is this piston continuing this cycle as well, but it's just good to bear in mind that we're talking about fluid dynamics here, and there's just some mystery or some witchcraft to those dynamics. We've talked about the ECU controlling the amount of fuel that is burned in here. There's a very important ratio of the amount of fuel that we're burning, gasoline, to the amount of air that it needs, because we want, say we have 1 gram of fuel, it takes exactly 14.7 grams of air to completely combust the fuel and use all the air. The match is perfect. That ratio is very, very important, because if we have too much air, then we are losing efficiency, we're losing performance, because we could have burned more fuel. If we don't have enough air, then we're wasting fuel because some of that fuel remains unburnt. So what we're talking about there is called the stoichiometric ratio, which is the amount of air that should be burned by a certain amount of fuel. The ratio is 14.7 to 1. So if we, for example, had too much air going into the cylinder, we had more than 14.7, say we had 16 grams of air traveling into the cylinder along with 1 gram of fuel, then that would be considered a lean mixture, because we are putting more air than we need in there. On the other hand, if we put in, say, 10 grams of air and a gram of fuel, we have less than the ratio, less than this 14.7 to 1, then that mixture would be considered rich because we have too much fuel for the amount of air. So we're going to have fuel that remains unburnt. So that's the important number is, and we'll talk about this more when we come to fuel injection, but that's how the amount of fuel per unit of air is measured. It's important to notice though that we're talking about the actual numbers of molecules, or in fact kind of the weight. We're not talking about the volume. So 1 drop of fuel does not equal 14.7 drops of air. The ratio is vastly different because of course fuel is much more dense in liquid form than gases are. And there's one other thing, I promise, the last thing. This is a naturally aspirated engine. That means that it is simply relying on the suction from the piston and the flow of gases in there at atmospheric pressure to pull air into the system. There are forced induction engines where air is pushed into there rather than being pulled through, it's pushed in. Those use turbochargers and superchargers, and we'll talk about them in another video. The theory of the air intake system is actually all more or less the same. It's just that there's an additional force driving air in there.